seems to be happy. And let's go to the slides. All right. So this is a big potpourri of topics in this set of slides. It's about searching, sorting, and discovering how complex our algorithms are, which will definitely be the topic of CSCI 41 if you have to take that class too. So it'll be a little sneak peek before you take it. But let's get right into it. I guess I want to start with searching. And the idea of searching is you have a big pile of data. I guess I can leave this up. You have a giant pile of data, and you'd like to look through it for something. Like you have a big, you have a phone book encoded in memory and a vector or something, a vector of phone numbers. You'd like to look somebody up. So you got a big long vector. You can definitely generalize this, but let's just pretend you have a vector of numbers. And you'd like to see if that vector had the value 42 in it. You're not sure where it is, but you want to search for it, see if it's there. And this works for any kind of data structure. Search through it. Search through an array or a vector, search through a linked list. Hey, is there a 42 somewhere in here? Right? You can search through anything. Maybe it's the last new. But searching is just the idea of you have some data, you have a lot of it, you'd like to find something, see if it's there. Hey, does 42 exist? Right? It's a very common problem to want to solve. So let's talk about how to solve it. The easiest way, probably the most obvious way to solve this problem is to do what's called linear search. All right? So one way, let's pretend we're working with vectors/arrays right now. We're looking for something. If we want to find a particular element and we're not sure where it is, well, just check every index. Pretty easy, right? Checking every index means moving through the vector in a straight line. That's why they call it linear search. It's one of the reasons, at least. So here is my silly vector, 8, 6, 7, 5, 9, and I don't know, let's pretend we're looking for the 3 or something. So let's say here's our V, it's got all these indices, and we have a value that we'd like to search for, val to search for, and let's pretend it's 3, right? So we're not sure where it is, so we have to look through the whole vector. Look at index 0, is that 3? Look at index 1, is that 3? Look at index 2, is that 3? It's pretty obvious, right, how you do that? And eventually you'll stop at index 4, okay, I found it. All right? And so that's the name of the game is linear search, and it returns to you the index where you find the thing, if you can find it. So linear search, it's like a function. It takes a vector or an array, it takes what you're looking for in it, and if you find it, you return back an int, which is the index where you found the thing. So this particular call to linear search would return 4 because that's the index where the 3 lives. Otherwise, if you're looking for something that's not there, 42, then you'll search through the whole array, you'll see the last index still doesn't have what you're looking for, and you've discovered that it's not there. What index do you return in that case? You can just return -1. That's an index that never exists. That will alert the user that it was not found. All right? So that's going to be the problem. So let me, do I want to do it now or later? I don't know, let's just do it now. And then I'll do the rest of these bullets after that. So let's program linear search. Searching.cpp. So I'm going through a vector. I need vectors. Here's my vector. Not too bad. And let's linear search it. Cout linear search V for the number 3. What index does that live at? And let's do the same, but search for 42, so it should print -1. So that index doesn't exist. Right? And then now we go and make the linear search function. We should take our vector by constant reference because We're cool like that. We're not going to copy memory. We're not going to change it either. And yeah, the idea of linear search is go through the whole thing, go through every index, like in a straight line, every index from left to right, looking for val to search for. Okay, that's what you do. Oh, sorry, I spelled vector wrong. That fixes it. All right. So, okay, for int I equals 0, I is less than v dot size, I plus plus, those would be all the indices of v, right? I'm going to look at that particular index, see if I find what I'm looking for. And it'll always return if it finds the first thing. Like if there's 2 3s in this vector, it'll return the index of the first thing because we're looking from left to right. So if v at I is equal to the value that I'm looking for right now, then I found it. I need to return the index where I found it. And that's just I. Okay? So if we find it, we're going to return sometime in this loop, and the function's going to be over. Otherwise, if we stop and the loop is over, if we get here, then we didn't find it. All right, we exhausted every option, went through the whole vector. Sadly, we didn't find what we were looking for. In that case, let's just return -1 to mean we didn't find it. Okay, so that's linear search. Not too bad. And so it gives us back for -1 exactly what we expect. Looking for 3 and for 42. Are there any questions about this code? Not too bad, I hope. Just look through the thing for what you're looking for, and once you find it, return its index. That's linear search. And if you're not sure where in the vector the thing that you're looking for might be, linear search is the best you can do. You have to look through every index, right? Because you have no clue where the thing that you're looking for is. You have no information about the order of the elements. It could be anywhere. It could be at the front, it could be at the end, it could be anywhere in between. So it's the best you can do when you have no guarantees about how the things are stored inside of your vector. And that is definitely foreshadowing a future algorithm where we know a little bit more about our vector, we can do a little bit better and do our searching a bit faster. But linear search is the best you can do if you're not sure where the thing is. No guarantees about how your vector is ordered. All right. So with that, let's make a library instead of this. Let's get some practice making a library. So I'll make a searching.h file with the definition of linear search declaration, searching.cpp where I implement it, and then we'll use it in the main function, which I will put in main.cpp. So I'm going to split up what I just wrote. All right. So let's remove the compiled file, remove searching. So I'm going to call it main or something, probably. So I need searching.h. Searching.h. Did I spell that right? Yeah. So include your header file guards, and what should go there is the declaration of your function. That's going to be your library, our searching library. There it is, and we need vectors. And also, because this is a header file, we can't use namespace standard, so we have to say standard : vector v. Okay, so that's the header file. The CPP file is mostly the same. We don't need to include any of these, but we can include our library file, include searching.h. And that will, for us, include vector. And we're allowed in an implementation file to use namespace standards, so that's perfect. And then the main function can go in its own little file. Boop. Main.cpp. And that can include almost everything. We'll also have it include our searching.h file, right? Which implicitly includes vectors, because why not? I suppose usually you should include vector yourself, because you don't know what the library is giving you. That's unnecessary. So yeah, we've got a main file that includes our library. That's a declaration of linear search and uses it. We've got the header file, which is what it's the only thing that somebody needs to look at in order to tell how to use your library. It's just the declaration of all the functions in it. We've just got one right now. And then you have the implementation of the library itself. So everything that was declared in the header file, we are going to implement here just like that. And customarily, you include your header file in your CPP file. And because of that, we got vectors included for us for free because it got copied and pasted. All right, are there any questions about these 3 files that I just wrote? I don't know. Can I show them all to you at the same time? Header file, main file that uses it. We're good with that? Is it coming back to us? And then to compile, you got to bring all the implementation files together. You say G++, main.cpp, searching.cpp. The header file you don't need to add to G++ because it's getting copied and pasted every time you include it. Perfect. And I don't know, we'll call this main./main, and it does everything we did before. Okay? So any questions about any of this before I move on? All right, so to get us ready for a faster kind of searching algorithm, I have a question for us. We can just stay here, do it together. You can shout out your answers. But all right, let's say we're playing a guess the number game. I have picked a random number between 1 and 100. You don't know what it is. It's between 1 and 100, though. What is the best number to guess first? Somebody tell me. Why? Yes, that's true about 50, but why is that the best option? Why is the middle the best? In between? Somebody had their hand up. You want to? That's the answer I'm looking for. Good. It splits the range in half. So 50 is definitely the best answer. Because if you're not sure where this number is, right, it could have been small, it could have been big, it's between any of these, it's best to guess 50 first because look what happens. You have no information about where the number is or what it is, but the second you guess 50 and I tell you, oh, you might have got it first of all, but if you didn't get it, I would say, oh, it was too high or too low. And immediately, if I said it was too low, guess higher, you know that the number is over here. How many numbers did you just chop off? You don't have to look at it anymore. 50 numbers, right? Or I might be off by 1 there. But that's the best that you can do. If you guess anywhere else, right? If you guess 75, for example, I might not be guessing a high number. Maybe I tell you, oh, if you guess 75, that was too big. Guess lower. So you just cut off 25 and you have 75 to look through again, right? The best way, because you have no knowledge of where the number is that I'm guessing, the best way to guarantee that you cut off the most numbers each guess is to guess right in the middle. Okay? Are there any questions about that idea? You always want to you want to chop off as many numbers as possible, and the middle is the right answer there. Always guess the middle. And so then, if the number is between 50 and 100, then you do want to guess 75, right? If it's between 50 and 100, then your next guess better be 75. Okay? Similarly, like if you get in the shower and you turn on the water, right? I like to turn it all the way to hot so it heats up super fast. But then, like it's super hot now. I want to go in the middle. Is it too cold or is it too hot? Let's go in the middle between those two. Is it too cold or is it too hot? And you just go halfway each time, and eventually you'll get to the perfect shower temperature, right? So that's the same kind of concept. Guessing in the middle gets you somewhere very quickly. You don't need a lot of guesses to guess the number if you always guess in the middle. You need log base 2 guesses. Let's figure out what that is. Python 3 import math. Math.log log 2 of 100. So apparently you can always guess the number within 7 guesses if you always guess in the middle. You'll have to wait till CSCI 26 to learn why that's the right analysis. But that is my trick. All right. So with that in mind, let me teach you a new kind of searching algorithm. It's called binary search. Right? Again, it takes a vector and a thing that you're looking for in the vector, but this time, to use binary search, your vector must be sorted. Okay? Maybe you see where I'm going with this. But if your vector is sorted, you have guarantees about what's where. And the middle is a very interesting place to look first. All right? So, I don't know, 1, 7, 33, any sorted vector, 42, 55, 87. Here's my sorted vector. Whee. And let's say I'm looking for 33. And so it is in there. Now, just by being sorted, you get very strong guarantees about where an element is in a vector. Like the second you look at 7, you know that everything to the left of this index is smaller than 7, and everything bigger than to the right of this is bigger than 7. And that helps you cut off your searching space, your search space. That's the technical term, by the way. So, yeah, this is now a guess the number game. What's the best strategy to find 33? You don't know anything about the vector. You haven't looked at it yet. It's like it's a bunch of question marks to you, but you know that it's all sorted. Your best thing, your best job to do is guess in the middle first. So, I don't know, this is an odd number, or this is an even number, so there's no real concept of middle, so just pick one. Like let's say 42 is the middle of this. Okay? The second you look at 42, the second you look at the middle of your search space, the search space originally is the entire vector, the second you look at 42 and compare it to your 33, you know that if 33 is anywhere in this vector, it's to the left, right? It's nowhere over here. You just cut off half the space. Ooh, that's nice. So you know wherever it is, it's between like here and here, right? And then what you do, this is V by the way, you go and you search in the middle of your new search space. You know it must be between these indices now. Let's search in the middle of that. So you'll look at 7, compare that to your 33. Oh, it's bigger. Okay, that means now your new search space is, if it's anywhere in the vector at all, it's between here and here, right? And there's only one thing to check now, and you find it. Does that make enough sense? Any questions about that? So now it's better to start in the middle and always guess in the middle of my search space. Guessing from left to right is not ideal anymore if I know that it's sorted, and I can get there a lot faster too. Like if I had a size, I'll use Python again. If I had a size 100,000 vector and I was looking for anything, it would take me at most 17 looks, 17 checks of an index. I have to look at 17 indices to find whatever I'm looking for. That's a lot better than linear search, which would require searching through potentially 100,000 elements. Interesting. So this is binary search. It's very fast. Things get a bit faster because of this halving that you keep doing. Okay. So let me show you. Let me get closer to the actual algorithm now. All right. So your search space halves each time you make a guess, and so here's how you do it. I guess I'll just redraw it. Who cares? So here's our vector v. 1, 7, 33, 42, 55, 7. And let's say the value that we're looking for this time is 55. So this is index 0, 1, 2, 3, 4, 5. So the way that you set up your search space, so you know where you are looking through, you have two index variables. You have two variables that keep track of your low index of your search space and your high index of your search space. So initially, you'll set low and high to be the whole vector. So low is the 0 index and high is the last index. So initially, low is equal to 0, high is equal to 5. And then, so that means I don't know where it is. It's between index 0 and index 5. Just search through the whole vector. And so that's your starting search space. And then repeatedly, what you do is you find the middle element between your current low and high, the middle of your current search space. So you're going to do your first guess, your first index to look at. First guess is equal to 0 plus 5 over 2, right? What's the middle of those? Which is 2.5, but you chop off the 2, chop off the 0.5, so it's just 2. So your first index to look at, the middle of your current search space, is index 2, mid. So that's where you look. You look at the 33, and you compare that to your 55, right? And you notice the thing I'm looking for is bigger. So that immediately means that wherever the value is, if it's anywhere in the vector, it's between index 3 and 5. Does that make sense? We have just chopped off half of the vector. All right. So now, here's our new search space. I'll draw it in green. So we had 1, 7, 33, 42, 55, 87. We just looked at 33, so we know it's not there, right? So we don't even need to look at 33 anymore. The rest of the vector is here. And so now our search space, if we keep track of it using these variable indices, this is our low now. This is our new low, this is our new high, right? And then I think you can imagine that the middle of that is going to be this place. You'll look there and you'll find what you were looking for. Okay. So it only took you 2 tries. You looked at this index and then you immediately found this index, and that was what you were looking for. Whereas with linear search, you would have had to look through 1, 2, 3, 4, 5 places. That's quite nice. Any questions about that? So using that midpoint of your search space as a guide, you either change low or high. In this case, we had to go higher, so our low index changed. High stayed the same, right? And then for a reason, I'll show you, if low and high ever pass each other, given the rules that we're going to come up with, then that means our search space is empty. If low and high ever get past each other, like high comes before low or something, that is wrong. That means the search space is empty and we didn't find the thing we were looking for. But yeah, we cut off half the array each time super fast. All right, so let me try and prove to you that this is the right way to stop. Like if low and high pass each other, that means you're done. The search space is empty. So that is, let's draw a V. A lot of pictures today. 1, 7, 33, 42, 55, 87. And this is 0, 1, 2, 3, 4, 5. All right, so initially, let's pretend that the value we're looking for now doesn't exist. Let's pretend it's 12. And so, again, like low starts here, high starts here. The midpoint of that is going to be index 2. So there's your first mid. It's like mid 1 because we're going to do a bunch of mids. And then we compare our midpoint with the value we're looking for. Oh, 33 versus 12. 12 smaller, so it must be in the left half. All right, it must be between here and here. So that means highs are going to change, right? Low stays the same, but high changes to here. This is high number 2. Okay? And so now I'm searching between low and high 2, 1 and 7. Right? So you find the midpoint of that. What's the average of 0 and 1? 0 plus 1 over 2, integer division, that's 0. So that means mid 2 will end up being index 0, mid 2. And then you'll look at 1 and 12, and you'll be like, oh, it's bigger. So I need to advance my low index. Low needs to be higher than what it is right now. So that cuts off my search space between here and here. Just looking at index 1 now. So this is now low 2. So here's low, here's high. It's between index 1 and index 1. If it's anywhere, it must be index 1, given what we've just discovered. And so we calculate the midpoint of that, which is, of course, going to still be index 1. This is mid 3. Mid 3. And now we look at 7. Compared to 12, that means what we're looking for is bigger. All right, we know what to do when what we're looking for is bigger. We advance our low, right? We advance our low to be 1 more than mid, right? Just like we did here. So, all right, low becomes 1 more than mid. That means that low 3 is right here, but high 2 is behind it. Okay, so that indicates to us that our search space is empty. Low just passed high. That means what we're looking for is not there. Okay? Does that make sense? Any questions about that? It'll make even more sense when I program it, but that's the idea. And by the way, it does have to be 1 more than your midpoint, because it makes no sense to check that again. All right? Here was your original thing between low and high. You looked in the middle of that, and if it was too small, like your original search space was this, if it was too small, you got to check higher. You know that it wasn't your midpoint. So it's always your low, your new low is here, which is equal to the old mid plus 1. So now you're searching between here and here. Okay, that's the idea. This was supposed to be mid. So with that in mind, let's implement it. So you start off your search space, your low index and high index. It's 0 and v.size minus 1, and then forever, repeatedly, until you get to either you find the thing you're looking for or you have an empty search space. Find the middle, check it. All right? So let's program this together. Let's see. I want to do it. Here's the declaration. I'll copy that into the header file. That was nice. Remember, it's standard : vector. And then in searching.cbp, there it is, we go and implement it. All right. So, initially, our search space is the entire vector. Which means the low index is index 0. That's the smallest index that it might be in. And then the high index is v.size minus 1. That's the largest index that the value might be in. All right? And now you want to keep on searching. While low is less than or equal to high, I still have a valid search space, right? So keep searching as long as low is less than or equal to high. As long as low is still to the left of high or equal to it. All right? So I have a valid search space. What I need to do is look in the middle of it. So check the middle element between low and high. So int mid is low plus high over 2. And then the value at that location, int mid val, is equal to the at mid. Okay, so this is the thing that's actually there at that middle index. And I want to compare that to the value that I'm trying to find. Maybe it was 55, right? So if the value that I'm looking for was less than mid-val, what does that mean? Which example was that? If the value that I'm looking for is less than mid-val, if I'm in this kind of case, I'm looking for 33 and I'm seeing 42, that means that low stays the same, but high should be 1 less than mid. Okay, the high index changes because I need to look to the left. All right? So the value I'm looking for is smaller. I need to look to the left. All right? So that means change your high index to be mid minus 1, because we just looked at mid. It's not there. Don't consider mid anymore. We don't need to. All right? Else if val to search for is greater than mid val, that means the value that I'm looking for is bigger. that means we're in this kind of case. We see 33, but we're looking for 55. That means that the low index should change to be here, one more than the mid. Does that make sense? So, the value I'm looking for is bigger. I need to search to the right. So low becomes mid plus 1. All right? That's how that's going to work, just like this. Here's the old mid. It was too small. It should be plus 1. That index plus 1. And then else, what's the only other option? If it's not less than the value I'm looking for and it's not greater than the value I'm looking for, if I get to this case, I found it. I found what I'm looking for. We found what we were looking for. It was, we have to give back the index as usual, right? It was at index mid. That was the middle index, and that's the one I was looking at right now. I found it there. So return mid. All right? And that's pretty much the algorithm. If low ever passes high, we're going to jump out of this loop, and that means the search space is empty. So if we ever get out of this loop, that means we didn't find it. So if we get here, low passed high, that means we didn't find it. All right, so we'll return -1 to indicate that it wasn't there. Okay, so that is the algorithm. It's a bit fancy. Please study it, but we can use it now. Let's use it in main. A lot of this. This will be what, V2? I need to give it a sorted vector. So I'll do that. 7, 33, 42, 55, 87. And let's look for all the things that I was looking through. Let's call it binary search, of course. Oops. Through V2 for, it was 33, 55. We looked for 12, it wasn't there. And then we can look for anything. Look for 87, look for 1, look for 42. If we look for 42, we're going to find it immediately. So let's look for that one. So that's all those. And let's give some space in between these so that we can actually understand the output. So this is saying, all right, I found 33 at index 2, perfect. I found 55 at index 4, awesome. I found 12 nowhere, so -1. And I found 42 at index 3. That's actually, that wasn't the first one I checked. It's always 33 is the first one, isn't it? So that is binary search. That is this algorithm. Okay, so there's a lot going on there. Are there any questions about what I just did? Do you kind of see how it matches my words, diagrams? It is a weird one. All right. We're good to keep going? So binary search, just this idea of checking in the middle and like going higher or going lower, is a common thing in computer science. Binary search is a great example of it. Another example that I'm going to give to you in a future lab, I can't remember if it's this one or not, it'll be a future lab though, is I'm going to ask you to program a square root calculator. So you give a number, I give you a number, you calculate the square root for me. All right? So here's a question for you to discuss with your group right now. And then we'll come back and talk about it. But let's pretend we are searching, right? It's a search problem. Let's pretend we're searching for the square root of 49. And you guess, right? Square root of 49. You make a guess that the square root of 49 is equal to 5. Of course, that's not correct, right? Right? But I would like you to figure out, how could you tell me, how do you figure out if your guess, like if it was 5, it was too low, right? If it was 10, it was too high. How can you tell, without actually calculating the square root, if that guess was too high or too low? Without knowing how to calculate the square root. That's my hint. Right? How would you say, all right, I think it's 5, but no, it's too small. If I told you I think the square root of 49 is 5, how would you argue to me, without actually going and calculating the square root, that it was too low? All right? So discuss that as a group and see if you can figure it out. You're not allowed to type square root of 49 in the calculator, though. How would you do this without knowing the square root? You just know that it's supposed to be the square root of 49. Take another minute to discuss. Likewise, if I claimed that the square root of 49 was 10, how would you be able to tell me, without calculating the square root, that that was too high? All right. Did we come up with any ways to do it? What could we turn this into if we're not allowed to calculate the square root? How could we discover that this is too low? Any good ideas? Yeah. Yeah. That's perfect, yes. So look at what you can transform this equation into if you square both sides. This now becomes a question, is 49 equal to 25? How does that compare? And now you know that it's too small, right? Conclusion, guess higher. Does that make sense? With that in mind, you can calculate the square root of a number by making guesses. You can always get closer and closer, improve by half each time. So you can make a function, like called square root, takes some number and returns back the square root by guessing, all right? And here is how you do it. Your initial guess for the square root of the number is, like, you know, wherever the square root is, it's between 0, like it's always a positive number, right? It must be between 0, or non-negative that is, and the maximum of 1 and x. You have to do this because, like, if you're asked to calculate the square root of 49, you know that the value is between 0 and 49, right? Whatever it is. That's easy to understand. But if you're asked to calculate the square root of like 0.25, you cannot say that the answer is going to be between 0 and 0.25. Because if it's smaller than 1, it gets bigger. Do we remember this weird quirk of square root? The square root of 0.25 is 0.5. So if you've ever seen a number between 0 and 1, just say that, all right, the upper bound, it's between 0 and 1. Just do 0 and max of 1 and x. That'll be the right way to do it. With that in mind, you have a starting bound for where the square root is, right? You got a lower bound and an upper bound. Now you can start guessing. Does that make sense? So you just repeatedly look in the middle of your search space and make it bigger or smaller as needed. So let me show you the square root of 2. Let's try to calculate the square root of 2. So here is a graph. Here's the square root graph. Here's the square root of 1, which is 1, right? There's 1. And then here's the square root of 2. That's like 1.4, whatever. So like here's 1, here's 2 up here. The square root of 2 is not quite that, but our initial guess, right? Our initial guess for the square root of 2, we know that it must be, the answer must be between 0 and 2, right? The answer must be between 0 and 2, so that's our low and high initially. Okay. Then we look in the middle of that. We look at 1. Right? So our first midpoint is 1. Mid 1. We look at that, we see 1, and we compare it. That's our guess. Our guess right now is that 1 is the square root of 2. And we look at that and we say, all right, how close is that? Is that right? So we square 1, square the square root of 2, compare 1 and 2. It was too small. Right? So 1 is too small of a guess. So our new search space is between 1 and 2. We just halved the space for where the square root of 2 must be. Right? We take our mid and we square it. Right? We compare it to our value. All right? Otherwise, we move around like this. The low becomes, the new low, there's no concept of like plus 1 or minus 1 here. The new low becomes 1 itself. This is low number 2. And now our midpoint is 1.5, right? 1.5. And so you take 1.5, that's your new mid 2. Mid 2, you square that. Because we noticed that 1 squared, that was smaller than 2. We need to guess higher. And now we guess 1.5. That's our new midpoint. So you say 1.5 squared. How does that compare to 2? It's actually bigger. Oh, shoot. 1.5 squared is 2.25. That's a little too big, so we got to guess lower than that, which means that our upper bound needs to change. Now the high becomes here. This is now high 2. And so now wherever the square root is, it's between here and here, right? And so we've cut it to be between 1 and 1.5 at this point. And you can keep on getting closer and closer and closer until you have a guess that is close enough to 2, because then you'll have close enough to the square root of 2, because then when you square it, it's going to be pretty much equal to 2, right? And that's when you stop. Does that make enough sense? So you keep on having your search space. You repeatedly check if the middle is close enough to the square root by squaring it and looking at how it compares. If it's ever close enough, this is doubles, by the way, so you can't check for equality. You have to check for, like, is it really, really close? Is mid squared really, really, really close to the x value that I'm trying to take the square root of? Like if it's less than 0.0001, it's fine. In that case, you can pretend that it's the real square root. Otherwise, it's either too big or too low. All right, too big or too small. So if mid squared was too low, you got to guess higher. So low equals mid. Otherwise, if mid squared was too high, you got to guess smaller. So high is now mid. All right. So this is the idea that you will eventually be implementing in your lab. I just want to give you a taste of it. And let me draw it out one more time. I'll explain it even more when I release that lab. But here's the idea. Example of calculating the square root of 2, just with numbers, not with graphs anymore. So, all right, here's our x. Our x is 2. We're trying to calculate the square root of 2. So we have lows and highs, right? Our low and high start out as 0 and 2. Wherever the square root is, it's between 0 and 2. So we calculate the midpoint of that, which is 1, and we check it. How does 1 squared compare to 2? Because that was supposed to be the square root of it, right? So if we squared it, should be 2. But that's a little too small, so our decision that your program's going to make is guess higher. All right. Next, all right, that means if we're guessing higher, our search space better be between 1 and 2 now. Our old mid is now the low. All right, so the midpoint of that is 1.5. Compare 1.5 squared to 2. That's a little too big, so we guess lower. Guess lower. And now our lower bound stays the same, but our high is now 1.5. It's the old mid. And so now our new midpoint of that search space is 1.25. And we're always making sure that our search space contains the square root somewhere, right? We're getting closer each time. 1.25 squared, compare that to 2. It's a little too small, so we guess higher. Because 1.25 squared is 1.5, 1.6. It's not quite 2, so we've got to guess higher than that. So that means our low needs to change. It's definitely not 1, it's bigger than 1. But it's between 1.5 on the upper half. So it's between 1.25 and 1.5 now. We're getting closer and closer to the real square root every time. And now you calculate the midpoint of that, you check it, like figure out where you need to go. Eventually, with enough checks, you're going to get closer and closer and closer to the real square root of 2. And the second that it becomes close enough for doubles, close enough within like 0.00001, you can pretend that that mid value really is the square root and return that. Okay. Are there any questions about this process? It's very similar to binary search. That's the idea. All right. Yeah, any questions about this before I move on to a completely different topic for the rest of the day? So the final topic is a thing called makefiles, which is going to make our life so much easier. So normally, right, when we compile, we use G++, right? We have a bunch of programs that we'd like to give to the compiler. So we have searching.cpp. We've got main.cpp. We give those all to G++ usually, but really a compiler is supposed to translate a single program to binary, to machine code, to object code. So G++ has been doing some extra work for us under the hood that we didn't really care about until now. A compiler just translates a single program to machine code or object code. So really, G++ is just taking one thing at a time. It's making like searching.cpp machine code. It's making main.cpp machine code, and then it's calling the linker for you. The linker is what combines your programs together so you can have a bunch of stuff. So it gives your main program, it gives your searching library, it gives IOStream that's already been compiled on your machine. It's bringing those all together in the linking stage. And that's what gives you your final program. So it's a combination of compile an individual program to object code and then link it all together at the very end to give you your final executable that you can then go and run. Okay? So only after both, after compilation and after linking, you have something that can be run. It's all together at that point, right? So we've been using G++, then the name of the file, all together. Like we've been giving G++ all these files, right, that we've been working on, and having them compile them all at once, right? Please G++ compile main, compile searching, link them together, call it main. You might eventually ask the question, if I change just one file, oops, I gotta get rid of this. If I change just one file, and I have a bunch of files that I'm working on, do I have to recompile them all? Like that's what this line is doing. I had x.cpp, I had y.cpp, and I had z.cpp, and those get compiled to object code, right? Whenever I compile them with this, secretly G++ is doing something like this. It's making machine code for x, just for x. I'll call that .o for .object code. So those are like the ones and zeros that make up the x library. That's what's happening there. Same with y. Y gets made into y.o. That's the binary form of its code. And z.cpp gets made into z.o. That's the binary form of its code. All right, and then finally, G++ is linking it all together. It's calling the linker and calling the final executable blah. So they all get linked together at the very end, call it blah. And let's say you made, this line does all this, right? It creates the object code, it links together. Let's say you made a tiny little change just to x.cpp. You didn't touch y or z. If you used this, G++ is forced to recompile x.cpp, which really does need to be recompiled, but it's also going to recompile y and z to the same thing all over again and link it together. That is inefficient. That's silly. We don't want that, right? Oops, let's get rid of that too. Don't need that anymore. You just need one single file. Like that. This is silly to go through this stage. Let's have G++ explicitly make these .o files so that I can make sure that I only am recompiling the things that need to be recompiled. Okay? That's the idea. So you can have G++ make these intermediate object files for just those single files, those single programs, by using the -c option. That'll create the .o file for you, right? -c stands for compile only, please. Compile only. All right? And that will make the new x.o file, which is nice, machine code. And then you can do the same thing for y.o and z.o. And you don't have to change them. You'll just link them together at the very end. Only x needs to change. Only x needs to be recompiled, all right? And it's supposed to be in this compiled form of just x.cpp. That's what I mean by x.o, right? And then finally, to link, I thought I changed all this. Sorry about that. I'll have to go back. To link, you just give all the .o files to G++, and it will link them together for you. So you say G++ with the .o files now, and give it the final name, and that will perform just the linking process. Because all these things are already machine code. They've already been compiled. It knows that. Z.o, and then apparently this is going to be called exec file name, whatever you want it to be called. That's the linking process. So G++ knows just to link if they're already compiled. This is linking. All right. And so let's do that for our searching library. Ready? Instead of, let's get rid of main. Let's make .o files. Let's say G++ -c main.cpp. All right. You don't even have to do the -o. It automatically makes main.o for us. Let's do the same for searching.cpp. G++ -c searching.cpp. Boop. And that makes searching.o. And now I'll link them together with G++ one last time, main.o, searching.o, and call that main. All right? And it does the exact same thing as we were doing. But now watch what I can do. I can make a change to an individual file, like instead of searching for 42, let's search for 87. So I've only changed main.cpp. I do not need to touch searching.cpp, right? I don't need to touch searching.o. I don't need to recompile the searching library. I only changed main.cpp. So that's the only thing I need to recompile. So I'll just say G++-c main.cpp and relink with the new main.o and the old searching.o. Oops. And now it's looking for 87. And that's index 5. Does that make any sense at all? So I'm separately compiling all these things. That's the process. It's called separate compilation. And once you get to industry, you're working with a million C++ files all at once. You do not want to recompile every single one of those million C++ files if you make just a tiny change to only one of them. Because compile times take hours with a lot of files. Right? We've been very happy with our few files, though. So this is what you want to get interested and start doing, right? Get interested in and start doing. You would like to separately compile all your things into these .o files and link them together at the very end, so that you only need to recompile what changes. Are there any questions about that? Your next comment might be, all right, this is nice. I don't have to recompile everything, but like I have to do -c so many times now. Like that seems like a pain. So my last thing that I want to show you today is something called a makefile. You make a file in your directory. A makefile it has a different language. This isn't C++ anymore. You make a file called makefile, like that is the name of the file with a capital M. You put that in your directory and it looks like this. And then you can just say the word make on the terminal and it compiles everything separately. It uses the .o files, it links them together, it notices what changes. It will automate the compilation process. So you never have to use G++ again if you make a makefile. It'll do it for you. It automates the compilation process. So this whole thing would be set in a file called makefile. That's where you put it. And what a makefile does is it contains little recipes for how to compile your programs. Like, all right, I want to make main.o, I need main.cpp, here's the G++ command for it. Man, why is it doing that? Everywhere, I got rid of it, but here, I guess, sorry. I need to do all that. This is my G++ command. If I want to make foo.o, I need foo.cpp, and here's what I do. If I want to make my final program and call it prog, I need these two .o files, and here's how I use G++ to compile them all together and link them. Sorry, just link the compiled files. Okay? And comments in a makefile start with a number sign, like Python. If you've used Python before. But once you have this, you no longer need to say G++ anymore. It will say it for you. It will notice what changes and only recompile the changed things. Makefiles are lovely. All right? So I'm going to get us into the habit of using them. I'm going to teach you how. I guess this time I'll just give you an intro, and then next time we're actually going to make a makefile for our library that we made today. So here's the example. So a makefile has a bunch of these little recipes, a bunch of little rules about how to make things, how to compile stuff. But let's use a food example, because it really is kind of like a recipe. A makefile is made up of a bunch of rules, and here's an example rule. It's got a name. We call that thing a target. Like, what do you desire? What do you want? That's called your target. You say that first, and you put a colon after it. And on that line, you space separate all the ingredients that you need to make your target, all of your requirements. So in order to make my target name, I need requirement 1, requirement 2, requirement 3, all the way to the end of the line. So that's the first line. And then you tab over. Boop, boop, boop. This is not spaces in makefiles. It's actually a tab for once. It has to be the tab character. And then, as long as you're tabbed in, you can give as many lines as you need to list all the steps you need to do to make that target using these requirements that you know you must have. Okay? So that's the setup for how to use all these rules. But let me show you how to use the makefile rules to create like a peanut butter and jelly sandwich. So the thing that we want, let's call that PB_J, peanut butter and jelly sandwich. That's what we desire. That is our target. All right? What are the ingredients that are required to make a peanut butter and jelly sandwich? Well, you need peanut butter, you need jelly, you need bread, right? You need a knife, maybe even a plate. But that's your ingredient list. You put those after the colon, space separate them, and then you tab over. And then you list all the steps that you need to use these ingredients to make this target. All right, so I don't know, open peanut butter and jelly jars. Let me write this slightly nicer. Open peanut butter and jelly jars. Get 2 slices of bread. I think you can imagine the rest, right? All the steps that you need to make a peanut butter and jelly sandwich. It's like a recipe. And the beauty of a makefile, though, is it's going to look at all these requirements, and it's only going to run this rule to make peanut butter and jelly if you have all your ingredients. If you do not have an ingredient, the wonderful thing that a makefile will do is it will look for a rule to make that. So if you don't have peanut butter in your cupboard, it will look for a rule called PB. And what are the ingredients for peanut butter? Well, I guess you need peanuts and a blender. You tab over, blend peanuts, put in jar. That's the rule for peanut butter now. And if the peanut butter and jelly rule, which you really wanted to run, notice that you didn't have peanut butter, it would go and run this rule to create peanut butter for you. That's the magic of a makefile. And then if you didn't have jelly, or if you didn't have bread, for example, what are the ingredients for bread? Flour, water, yeast, all that stuff. Let's just make it easier. Ingredients for bread is money. Then you just go to the store, buy bread. Go to store, buy bread. Now you have bread. And so you can run all these rules, and that tells you exactly how to create something, all right? So that's what makefiles are good for. Here's the structure of the makefile. It's always your target, the thing that you're looking for, the thing that you want, the requirements, what you need in order to make those things. Then you give a bunch of, these are terminal commands, really, in a makefile. Terminal command to partially make it, terminal command 2 to partially make it, and eventually you'll end up with usually a G++ call in this class to finally create, after doing a bunch of stuff maybe, the thing that you're looking for. And usually it's got the same name as the target, all right? So these requirements, you can also think of them as ingredients. All right? And so, for example, if I want main.o, this is exactly how you would write this rule. If I want to make main.o, I require main.cbp to exist. Otherwise, there's no use trying to make a .o file from a non-existent CPP file. And the way I tab over, how do I make main.o given main.cpp? Well, I use G++, G++-c main.cpp. That's the rule. That will make main.o. And the makefile will do it for you if you ask for it, right? So yeah, the beauty of makefiles is it knows when things change, and I'll show you this next time. And they know how to make those requirements if they don't exist already. It'll go and look for a rule for those, right? So if anything changes, make is only going to rerun the relevant rules. And this is all coming down to, this is the final product, essentially. The idea is there's a command line program called just make that looks for a makefile. It just automatically finds the makefile in the current directory. And you say, I want to make main or something, whatever the rule is, so you hit enter, and then it will find it for you, all right? There's also some default rules that it's trying to run right now. I'm glad it didn't overwrite anything. So you can just say make the name of your target that you care about making, and it will run that rule for you, which might do a million things, but you've already placed that in the makefile. So it's all automated. It's all wonderful, okay? So that is my motivation for makefiles. I'll show you a real one, and we'll actually use it on our library that we made today. Next time. Are there any questions about any of this for now? So I think the final thing that I wanted to do today was show you your next lab. So this is lab 9, do week 15. We're getting to the end. There's only 17 weeks of class. This one, though, no square root just yet. I think this one's before it. This one's about recursion. All right? So let's get our starter code. Let's take a look at it. So it's these 3 files. All right? So recursive funcs.h is the declaration of all of our recursive functions that I'm having you write. You've got is palindrome, sum digits, and string length. Those are the 3 things that you're going to be creating. Is palindrome returns whether or not a string is a palindrome. Sum digits adds up all the digits of a non-negative number. And string length takes a C string, not a C++ string this time, and calculates its length. How many characters long is it? All right, so those are the 3 recursive functions that you're going to be implementing. And you'll implement them, of course, in the .cpp file. And actually, is palindrome I've split up for you to be like an initial function and then the recursive portion of it. I'll talk about that in a second. But yeah, that's is palindrome. Here is sum digits, string length. Here's where you'll implement the recursive version of palindrome. And here's the original is palindrome that's going to like fix up the string and then call the recursive function. All right. So let's talk about palindromes if we've never heard of those before. So palindrome is just any string that's the same forwards and backwards. So like ABA, that's a palindrome. AA, that's a palindrome. Race car, that's a palindrome. It reads backwards. It's RACECAR, even if you go backwards, right? So for this lab, I also want you to pre-process the string. So get rid of spaces and capitals. So consider like A, B, a bunch of spaces, capital A. Consider this to be a palindrome. Okay? That's still a palindrome. Race car with some weird capitalizations and spaces, that's also a palindrome. So what you need to do is clean up your string before you give it to the recursive function. All right? So the first function is called isPalindrome. That's the original function that the user is going to call. You will clean up your string to be like normal lowercase race car without spaces, for example. You want to remove spaces, make everything lowercase, and then you'll call isPalindrome recursive on that nice pre-processed string. All right? So isPalindrome cleans up the string and then calls isPalindrome recursive and returns that result. Okay? The result of this recursive check whether the pre-processed string is a palindrome. And here is how you can recursively figure out if a string is a palindrome. So here is race car. If this is a recursive algorithm, and it must be, I'm claiming that it is, you must find a smaller palindrome checking problem inside of the bigger palindrome checking problem. Does everyone see it? If a race car is a palindrome, that must mean that you have to check some things on the ends, and then the inside, maybe that's also a palindrome. Something like that, all right? You'll need to find the smaller palindrome checking problem inside of each string. And then there are multiple base cases because a string can be either odd or even length. You're going to have two base cases. Here's the question that you'll ask yourself to figure out what the base case solution is. So which strings do I immediately know whether or not they're a palindrome? They're really small. Think about those. All right, and so that's the palindrome problem. You're going to clean up your string. So if you get a weird looking one, you get rid of the spaces and the capitals. Then you call the nice recursive version of the answer. Right? Call the recursive function to recursively check if your pre-processed string is a palindrome. And so you'll have to chop off like the front character, the last character, make a recursive call, stuff like that. Any questions about that? So it takes a string, gives back a bool, whether or not it was a palindrome. You good with that one? That's probably the hardest. The rest look like this. The next one's sum digits. I would like you to sum all the digits of a number. So for example, if the user calls sum digits on 1,234, you need to give back 10 because the sum of all those digits, 1 plus 2 plus 3 plus 4, is 10. That's what I mean by summing the digits. All right? So here's a hint for the recursive case. Here's the smaller problem. You can break it down into everything, into like solving the problem on summing the digits of just 123. That's a smaller number, right? And then you can add in the 4 later. That can be the final step. So that's how you can break it down for the recursive case. I want you to think about the base case, what that might be. And then finally, C string length. So sum digits is get a number, return a number, that's the sum of its digits. And then string length is given a C string, calculate its length. All right. So for example, string length of ASDF, that string should return 4. An empty string is length 0. All right. So you need to figure out like where's the smaller string, how do you extract it? You'll have to do that pointer arithmetic stuff that I was talking about before in the previous lecture. Remember that S is a pointer to the first character in the string. That's how you represent a C string. It's a pointer to its first character. And the final character, the end of the string, is that null terminator character, right? So that's what you'll be looking for. And so here is a hint for the recursive case. So you're trying to get the length of the string hello, that's a C string. The answer is 5, and that breaks down to be, well, it's 1 plus, because you know it's a bigger string, 1 plus the length of the smaller string. 1 plus the length of just hello. Yeah. And the base case is going to be the empty string. The length of an empty string is 0. All right. So those are your recursive functions that I want you to write. Are there any questions about those? And so I've made a bunch of tests for you in the testing files, but you're not going to add any of your own. You're just going to turn in recursivfuncs.cpp. But please compile and run the test file so that you can make sure that your stuff is correct. Here they all are. Testing for a bunch of different palindromes, things that are and are not palindromes. Testing for digits. Testing for string length. Yay. All right, so get those passing, and that will be all. Those are your 3 functions. Really, palindrome is secretly 2, but that's the idea. All right. Any questions about this or anything else that we talked about? All right, that's all I got.